and they're on TV. That's good whenever they're on TV and they win. It's bad whenever they're on TV and they, you know, lose by a lot. But that wasn't the case. Okay, so Wednesday, this past Wednesday, we were talking about bonding. We did a little bit of a review of bonding. Today, what we're going to do, and so when it comes to bonding, we've talked a little bit about like what does a molecule look like in space? We are going to take that a little further. And one of the ways that we're going to take it is we're going to say, all right, well, sure, this molecule exists in three dimensions. Am I recording? Yes, I am. Sure, this looks like in th sure, we have this idea of what it looks like in three dimensions, but where are these things in three dimensions? That's what we're trying to figure out because the more that you know about the space that a molecule occupies, the more that you know what something looks like, the better off you are in terms of understanding how it's going to exist and how it's going to like behave, I guess would be a good phrase. Um, and I think that that's yeah, so that's what we're really getting after. And this is super important stuff because um, go ahead and add to the chat if you ever had a PlayStation 3. I did. Here, I'll add that to the chat. I did. I had a PlayStation 3, and I think I had like three games for it. Guitar Hero 2, I think, and then I just had like a couple of Blu-rays. So it was really more of a Blu-ray player. Um, but I bring up the PlayStation 3 not just because it was a video game system. Video games are they're fun. And I'm among my friends, I'm notoriously bad at video games. And the reason for that is because I'm not really much for video game stories or directions. I'm more of like a Super Mario Brothers, you run and then you jump and then you like get the bad guy. But I bring this up all because on the PlayStation 3, there's this piece of software that would run in the background. And when you had your PlayStation on and you were not playing a game, the processor would run these computations to predict what a protein looks like. And if we've probably heard of proteins and definitely like a whey protein or something like that. But proteins and knowing what proteins look like is a huge part of the study of biochemistry. And as a huge part of the study of biochemistry, it's a huge part of health. Now, when it comes to like, if you're familiar with Alzheimer's disease, well, Alzheimer's disease is when a protein, a specific protein, doesn't look like how it should, and instead takes this different shape. So when it takes this different shape, that's whenever it causes a disease. Um, So in the PlayStation 3, they would run this program that would basically do these really complicated calculations to see what does this protein look like. Because when you know what a protein looks like, then you can say, okay, well, I see there's this little cavity in it, this little curvature. I'm going to design a molecule that basically sits in there and blocks that protein from doing anything. And therefore, if I can block that protein from doing something, then it prevents a disease state from coming on. So that's one of the important parts about like understanding what a molecule looks like in three dimensions. Now, we're not getting into protein structure, but we are getting into what do small molecules look like in three dimensions. So what we're getting into is like simpler molecules. And this is where everyone starts. Whenever you're learning about protein structure, you start with, well, what does this carbon do? What bonds does it form? How many bonds does it form? And you get a little bit more information about it. So we're talking about molecule shapes, and we're going to dice this up today, Monday and Wednesday, and then a week from today, we're going to do a review. So when it comes to molecule shapes, Lewis dot symbols for our main group elements. We've seen this before. I showed you this slide a handful of times. And the important takeaway from, Oh, what? Something just happened, and I didn't want it to happen. Just a second. Bear with me, folks. Yeah, continue presentation. That's what I said. Okay, I apologize for that. I'm getting mad at my computer. I'm not getting mad, but, confused. So the important part of this, I think I must have pressed the button. The important part of this was we were looking for numbers of valence electrons. And I want you to be able to take this table and kind of project this or extrapolate this over the table that is your over the periodic table. So we've got group one, group two, group three, which is also 13, group 4, 5, 6, 7, and your noble gases, which correspond to 14, 15, 16, 17, and 18. Let's see a chat. Good morning, Aurelia. How are you doing? Excellent. So, thank you for your greeting. I always like your morning greetings. So, we've got these different groups, and they correspond to valence electrons. If we take something like oxygen, oxygen is in group 6A, and it has 6 valence electrons. If we look at our noble gases, those are in group 18, and those have 8 valence electrons. So what we're going to do is our first question. How many valence electrons does Cl have? Now, the important thing to think about with this, and I'm going to go ahead and start the question, is before you answer this, remember, this is Cl. This is not Cl minus, because if I asked how many valence electrons does Cl minus have, it's a different answer. But this has, well, or how many valence electrons does Cl have? And actually, you know what? I'm going to give you a little bit of a hint. Cl minus has 8. And I'm really containing myself to not explain that anymore. If I did, then I'd give the answer away. But Cl minus has 8 valence electrons. So how many does Cl have is my question. Cortizan, are you trying it on the app? Hmm, that's interesting. Well, for these first few days with Top Hat, I'm going to be gracious and graceful when it comes to assigning points. So we're still in the launch phase, so I don't want anyone to get hung up on that. Okay, so that's strange. Okay, so the correct answer, 7. And 15 of you, great job. Okay, Cl versus Cl minus. Cl minus has 8 valence electrons. And that means that, and this negative charge indicates an electron. So that's where I got 7. So if I didn't have this negative sign, then I don't have that electron, and um, therefore you've got 7 total there. If you want to answer in the chat, that's fine. Go ahead and do as much. But I've got the I've got these top hat questions that are also assigned as homework, and that will close tomorrow morning at like 11. Go ahead and try to answer those. The course code is just a second. So it's just a second, folks. Oh, our course code is 8089958. Yep, 089958. Absolutely. I appreciate you guys' patience with the top hat. I'm confident that we're gonna get it all straightened out. Um, if it's not working right now. Yeah, absolutely. Yeah, definitely. Okay, so valence electrons are important because of the fact that they give us a sense of how many covalent bonds something can form. Now, remember, whenever we talk about covalent bonds, we're talking about sharing electrons. Okay, so if we look at something like oxygen, Blake, go ahead and answer the top hats in the chat. That's fine. We've got oxygen that loves to form one, two covalent bonds. Now, what this kind of projects out to is we've got these Lewis structures where we've got a Lewis structure like for water. Water has a central oxygen atom and then one and two lone pairs of electrons. But water also likes to form, or oxygen, I'm sorry, likes to form two bonds. So it has two bonds and two lone pairs of electrons. That's what oxygen likes to do. Ammonia likes to do three bonds and one lone pair of electrons. Methane likes to do four bonds with zero lone pairs of electrons. So if we look at our previous slide, we kind of see that in terms of, well, the bonds that something likes to form, and that's almost paired up with anything. So if we were to use this idea and say, okay, well, nitrogen likes to form three bonds. It's not necessarily hydrogen. Here's a molecule, and this is where chemistry can get pretty cool because you can have these molecules where you basically, it's almost like a hierarchy of needs. Like, how many bonds does carbon like to have? Carbon likes to have four bonds. Does this carbon have four bonds? There's one, two, three, four. Yeah, that has a complete octet. Nitrogen likes to do three bonds and a lone pair of electrons. Does this nitrogen have those three bonds and the electrons? One, two, three, and then here's our lone pair of electrons. Yes, it does. And you can see that it can form some pretty interesting and pretty neat structures, if none other, or if nothing else, like looking at them and being like, oh, crazy, it can form a ring. Carbon and nitrogens can form rings, and that's an important thing for basically DNA and the genetic material that makes you you. Now, the way that all these things kind of arrange in space is it's kind of it's kind of abstract, but it's pretty interesting. So there's a theory known as, or a theory of kind of rules, basically. It's called valence shell electron pair repulsion theory. I always like to simplify it and just call it Vesper theory. So Vesper theory is a basically a set of rules and ideas of how to coordinate or how to position all the different atoms and electrons in a molecule. Now, Vesper theory takes into account where atoms and electrons are in a molecule and basically what does that molecule look like in three dimensions. So here what we have are two different molecules. HCN. This is known as cyanic acid. This is basically cyanide. Then this one down here is dihydrogen because it's good. Um, it's a covalent or a molecular compound. Dihydrogen monoxide. Does anyone know any other names for dihydrogen monoxide? Dihydrogen, two hydrogens and then one oxygen. I'll give you a hint. You probably have had some today. A maybe more common name for dihydrogen monoxide. H2O, water. You're absolutely right. Okay. Now, what we're going to look at for this is, or what we're interested in whenever we look at the Lewis structure and this VSEPR theory, is positioning all of the different atoms and electrons within a molecule. So here what we have is the Lewis structure of HCN. Now, let's look at all of these atoms, and I'm going to add this lone pair of electrons right here. I'm going to look at all of these atoms and ask the question, does this have as many electrons as it needs? Hydrogen. Hydrogen likes to see two electrons. Does it have those two electrons? It does, because it brings one valence electron, and then it shares a valence electron with carbon. So hydrogen is happy. It sees those two electrons. Now, next up in our molecule HCN. Carbon likes to see eight electrons. It brings four of its own, then it borrows one from hydrogen. Okay, so there's one of the carbon electrons right here, basically. And then it's got three others, one, two, and three. And then it shares three more with nitrogen. So does that carbon have a complete octet? It does. So we'll give that a check mark. That carbon doesn't have any lone pairs of electrons. It gets its eight electrons by sharing them. Then, last but not least, is our nitrogen. Nitrogen likes to make three bonds and have one lone pair of electrons. And there it goes. It gets it through that. Now, what I want you to visualize and think about is, where are these atoms with respect to one another? How far away, or what's the angle measurement between this hydrogen and this nitrogen? Well, these are 180 degrees away from one another. It's almost like I took my two fists, and my camera can't show this, but my nitrogen is my right hand. It goes as far out, and think about my torso or my head as the carbon. The hydrogen is way over here. If I move my nitrogen towards the camera, what happens to my hydrogen? It goes into the wall back here. If I move the nitrogen up, well, then the hydrogen goes down. They are 180 degrees away from one another completely. Okay, now we're going to stop this, and we're going to look at a molecule shape and putting a molecule together. So with VSEPR theory, we're going to remove all these. What we're interested in is, where is everything surrounding this central atom? I want to make sure that everyone sees good. You see that? So let's say that we were to bond this central atom to 1, 2, 3, and 4 adjacent molecules. This gives us a way to visualize this molecule in 3 dimensions. All of these adjacent atoms are as far from one another as possible, but they're also kind of as close to one another as possible. They're all kind of like fighting to occupy the same space. Now, let's say that we got rid of one of them, 3, and we did something what like nitrogen likes to do. Nitrogen likes to make 3 bonds and then add one lone pair of electrons. If this bond right here is electrons, this bond right here is shared electrons, and then way back here is shared electrons. What do we know about electrons? Actually, add to the chat, what's the charge of an electron? What's the charge of an electron? Negative. Absolutely. What do we know about negative things around other negative things? And I can't help but whenever I think about that, I think about like um, people and personalities and like attitudes. Like if somebody has a bad attitude and they encounter another person with a bad attitude, they're like, ugh, that person's so negative. I don't like being around them. Yeah, negative charges do the same thing. They repel one another. Okay, so this pair of electrons and this pair of electrons, they're going to push one another uh, as far away as possible. Now, since it's just two shared electrons, they're going to arguably occupy the same space because these electrons, what they're going to do is they're going to gravitate towards either this atom right here, which I'll label as A, or this atom right here, which I'll label as B. The electrons that are shared between atoms A and B, they have a chance to, kind of go closer to A or B. Now, we talked about a property. It starts with an E. It's a property that basically explains the attraction that one atom has for electrons compared to any other atom. And I'll give you another hint. Fluorine is the most blank element. Close. Caitlin, that's awesome. It's so close. Electronegativity. So electronegativity is the property of like when we look at a bond and we want to say like, oh, this bond is, polar or something like that. Absolutely, Kevin. Electronegative. If we were to say that atom A is more E negative, then the electrons, they're not evenly shared between A and B. Instead, they're kind of closer to A. Okay. And if the opposite's true, well, then vice versa. So what we have and what we want to look at is those electrons, despite that, they're still being shared. Okay. So the electrons that are being shared between these elements, they're still going to kind of exist within a limited range. Does everyone follow me there? It's almost like, um, let's say that you've got two people and a dog. And the dog likes both people, but maybe it likes one of them a little bit more. Where's that dog going to run? It's going to run back and forth. That's going to basically kind of like burn out a little path on the ground between those two people. Chances that, we're taking into account like decently behaved dogs. And just so we're all on the same page, I do not have decently behaved dogs. I have really poorly behaved dogs. Um, and maybe that's the reflection of the owner. I'm not sure. I'm sure that there's lots of introspection that I could and should do, but here we are. So if this dog is an electron or electrons that are shared between these two people being this atom and this atom, well, that dog's going to go back and forth. That's kind of going to be reflected in this bond. Now, let's say hypothetically that there wasn't a second person. What do dogs do in wide open fields? Like and this is a well-behaved dog or a poorly behaved dog. If you open the back door and there's just a wide open field of bluebonnets, what's the dog going to do? Yeah, he he'll run. He will just go. Now, that dog is just going to, it's gone. Hopefully it comes back sometimes. And then if you stand at the back porch and you yell, "Dog, come on back." What's the dog going to do? It's going to be like, "Oh yeah, that's the human that gets me food. I better run back." I mean, I've been eating some field mice, which is great, but I need to go back. Yeah, he might. He might. You're absolutely right. My dog's pretty much 0.1% chance that they're coming back. Well, that dog is a lot like electrons in the sense that if that dog is basically being kind of confined to or gravitates towards one person, let's go ahead and here's our here's our two people. The dog's going to run back and forth between here and here. Would everyone agree that that's pretty much the path that the dog is going to take if it has two people to run between? Okay. Now, if if there's only one person, if there isn't that second person to kind of like call that dog back, you open the back door, dog's going to run out here. And then it's going to run out here. It's going to run out here. It's going to run out here. And then it's going to run over here. It's over there, over there. Dogs do still have like, oh yeah, you're the person that gives me food. So it's going to probably want to like keep you in eyesight. So it's going to still kind of like center back. It's going to come back. Boom, 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 boom. But we've basically got here, let me draw this on a, would everyone agree that if that dog is kind of like gravitating towards one person, and let's say that you let it run for a day, what that dog is going to do is just going to kind of go over and over all around in this space. It's over here, it's over there, it's over there, it's over here, it's over here. Would everyone agree that that's the dog's decision-making process? It's going to just run anywhere and everywhere that it wants. It will gravitate towards this person because that person's still going to give it food, but it's going to kind of go wherever. It doesn't have this second person here to like say, "Oh, hey, come towards me." So that dog's just going to go kind of bonkers. Now, I bring all that up, and this is a lengthy parallel, but it's an important one because electrons that are not shared by two atoms, they're going to behave like that dog that's let out into the backyard. And we've got that. We know those electrons as lone pairs of electrons. Now watch as I click this lone pair. What is it going to do? Well, it's gonna fill this kind of like it almost looks like a light bulb to me. Okay, so I'm gonna put that light bulb up top. Okay, so let's imagine for a moment one of the electrons is way over here. What do you think that does to the electrons that are shared along this path? It's going to have some impact on them. And what it's going to do is it's going to push them down. Electrons over here, it's going to push these down. So a lone pair of electrons basically repels shared electrons. And that's important to know because that's a part of a molecule's geometry. So let's go ahead and I'm going to clear all my drawings out. And I think that it's helpful. And for 20 something years, this is how I have thought about electrons and shared electrons and unshared electrons. But if specifically we can think about a water molecule, here's our central atom, two bonds. When there's only two bonds, those two bonds and those two atoms are 180 degrees away from one another. Does that make sense? Because basically those shared electrons here and here want to be as far away from one another as possible. Now, when we add a lone pair of electrons, whether they are shared or unshared, whether they are a shared pair or a lone pair, all electrons want to be as far away from one another as possible. So now I'm going to add this lone pair. Oh, that lone pair I mean, now it kind of looks like an alien from a movie from the 1950s. But that lone pair of electrons, they are going to occupy more space. They're going to be that dog that runs around, and they are going to repel any other electrons. Now, when I add another lone pair of electrons, the lone pairs of electrons will repel one another. They will also repel the shared pairs of electrons. This right here is what a water molecule looks like. It is what's known as a bent molecule. Now, if I add another bond, what happens? Now we've got three bonded pairs of electrons and two lone pairs of electrons. Now I want to go back into presentation mode. Start presentation. Oh man. Okay, there we go. Good. So this is the theory. The idea is that shared electrons occupy a certain confined space, and then unshared electrons or lone pairs of electrons occupy a different space. Now, here what we have is a water molecule, and the geometry that a water molecule takes on is what is known as bent. A molecule with nothing but shared electrons is a linear molecule if there are only two adjacent atoms. So when it comes to VSEPR theory, there's a lot to process, a lot of information to process. You have to think about, well, what are the atoms? Is there one that's more electronegative than the other? How many adjacent atoms are there? How many lone pairs of electrons are there? There's a lot that you need to process. Now that PhET simulator that we just went through, that we just were playing around with, I think that's very helpful because it allows you to look at a Lewis structure and kind of figure out what it has. So I believe here we go. When we look at a molecule, the question that we're asking is how many electron domains are there? Then, how many lone pairs of electrons? So if you want to think about this as, I always like to think about things as flowcharts. Your first question, oh, not a check mark. First question is how many electron domains? And that's going to be a whole number, 2, 3, or 4. Then, after you've figured that out, you ask the question, how many of those electron domains are for bonded atoms? Now, an electron domain, just to jog back for a second, that's basically just, well, you've got two atoms. Those would be two electron domains. If add to the chat, how many electron domains does water have? This is kind of working backwards, but how many electron domains does water have? Close. Electron domains. They can be bonded pairs or lone pairs. It's 4. Amira, great. It's 4 because 2 of them are lone pairs of electrons and 2 of them are, sorry, the other 2 are lone pairs of electrons. Now, if we jump back for a little bit and we look at this, I like this slide because it basically addresses a lot of information. How many electron domains does fluorine typically have? Account for the number of lone pairs of electrons and the number of bonds. And the key one I want to, Josiah, that's absolutely right. It's 4. This is a lone pair. This is a lone pair. This is a lone pair. So fluorine likes to have 3 lone pairs and 1 bond. So this is going to have 4 domains. What about boron? Right here. How many electron domains does boron like to have? 3. Absolutely. Okay. So for many of them, when you look at this slide, you might be thinking, well, Isn't everything going to be 4? It's close, but things can get kind of complicated because if you look at this figure right here, carbon likes to take on 4 bonds. Well, it can have a triple bond. So how many electron domains does carbon have in this atom? 2. 2. So this is where it can get kind of hairy and kind of complicated. But this, whenever you're kind of processing a molecule and you're thinking about, well, what's my answer? Ask yourself first, how many domains does a specific atom have? Then, how many of those domains are bonded? How many are lone pairs? Now, if a molecule has only 2 electron domains, those are going to be bonded pairs of electrons. There are no lone pairs of electrons, and that molecule is going to be a linear molecule. That means that those atoms have a good one. Good luck. That bonded or that angle between your atoms is 180 degrees. They're like my arms. They're as far away from one another as possible. They're pushing as much as they possibly can. Now, if your number of domains is 3, you're going to have 2 options. One option is all 3 of those are going to be bonded atoms, in which case you're going to have no lone pairs of electrons. And the shape of that molecule is what's known as trigonal planar. Some people pronounce that, and whenever I say some people, I mean a younger Joel Gray would pronounce that as trigonal. And I'm not sure why, but now I say it trigonal planar. All of the different atoms of that are 120 degrees away from one another. This is your trigonal planar geometry. If of your 3 domains, 2 of those domains are bonded atoms and 1 is a lone pair of electrons, that molecule is considered to be bent. Now, have we talked about a bent molecule previously? And if so, what was it? Or a molecule with bent geometry? Water had bent geometry. Does water have 3 domains? No, it's got 4 domains. Of those 4 domains, 2 are bonded atoms and 2 are lone pairs of electrons. This is a bent molecule. These atoms and lone pairs of electrons are 109.5 degrees away from one another. So let's see. You know what? We're going to do this last question, or we're going to do this question, and then we're going to call it a day. Just because this stuff is super abstract and super complicated. Actually, I think we got, let me see, just a second. Yeah, we got 2 questions. We'll do our 2 questions, and then we're calling it a day. Okay. Which is a non-polar covalent bond? And oh no, let me see if I can. You know what? Okay, I'm gonna add that. Thought that I copied and pasted that question, but I guess it didn't get in there. Okay, so what I'm gonna do is, here we go. I'm gonna switch my share, the exact same letter scheme as here. Um, or the answer options are the exact same. Just punch your answer in on either the chat or in um, whatchamacallit, Top Hat. This is the figure that you're supposed to see, our periodic table. we'll work through this one. And actually, this is going to be our last question for the day. So we are looking for a non-polar covalent bond. A non-polar covalent bond, what we're looking for is basically an electronegativity, a low electronegativity difference. So if we were to look at, now I'm going to switch over. Okay. Don't worry about it, Kevin. Okay, so the most popular answer was F, and that is correct. Okay. So when we look at our answer options, share this. So our electronegativity for fluorine. There we are. Fluorine has an electronegativity of 4.0. Fluorine's a great student. Hydrogen has an electronegativity of 2.1. Carbon has an electronegativity of 2.5. Nitrogen, okay, so that accounts for these first three. What's our difference between 4.0 and 2.1? 1.9. What's our difference between 4.0 and 2.5? So we just subtract those. It's 1.5. And then what's our difference between 4 and 4? 0. Now, one thing that I want everyone to be clear on is this is going to be an absolute value calculation. So it's never going to be like a negative number. So I set this up by just taking my larger electronegativity and subtracting it from my lower electronegativity. Wouldn't it be 2.5, not 1.5? Okay, so the 4.0, so this would be 4.0 minus 2.1, and then this would be 4.0 minus 2.5. So it's just the larger minus the smaller of the values. So yeah, 4.0 minus 2.5 is 1.5. Then for NH, okay, the electronegativity of nitrogen is 3.0. So this would be 3.0 minus 2.1. Oxygen has an electronegativity of 3.5 minus 2.1. Yes, Kevin, I will always give you electronegativity values for any calculation, anytime you need it. So then this is 3.0 minus 2.1, 0.9. 3.5 minus 2.1 is 1.4. So their correct answer was also the most popular answer of C. So yeah, that's how we solve this sort of question. Now, another way that this same question could be asked is, which is a polar bond? Or which is the most polar bond? And your answer for that would be A. Okay, everybody, that's what I wanted to go over this time. We're going to get into this a little bit more on Monday. We're going to start talking about individual molecules and looking at Lewis structures and classifying them based on that geometry. So if you are looking for something to do, like, oh, what would be a good thing to go over? I would go over, let me see it. It's loading. I would go over this table. Make sure that I know what an electron domain is and how an electron domain could be a lone pair or it could be a bonded pair of atoms. Okay, everyone. Well, I hope you have a great weekend. I'm going to stop my recording. I'll post this and then